Introduction and myself Nehru. I'm a postdoc fellow from Aarhus University. Today I'll be presenting one of our research group work which is on THz Spectroscopy study of stretched poly-L-lactic acid for piezoelectric enhancement. And this work was originally done by one of our colleague Youssif Merhi, and today I'll be presenting on behalf of him. So first I'll introduce the background and I'll talk about the PLLA polymer and the technique what we have used and the experimental setup, and followed by the result and discussion. So we all know that there is a growing need for biodegradable and sustainable materials across various fields, and these materials significantly reduce the impact on the society, and therefore like they are widely used in many biomedical applications. However, like we still need to improve the performance with respect to biosensors, and therefore, like we investigate the piezoelectric properties of PLLA film using THz spectroscopy. The main objective of our work is to improve the piezoelectric properties of the material and use it for the biosensor applications. So moving on to the properties of PLLA. PLLA is a semicrystalline polymer which is mainly obtained by the condensation of lactic acid, and it offers many advantages like transparent, flexible, and it is mainly present in many plants and fermented foods. It is like also biocompatible and biodegradable. So it's due to its tunable piezoelectric and mechanical properties. It is widely used in many applications like tissue engineering, drug delivery system, and medical implants and sensors. So first is that we want to improve the piezoelectric properties in the PLLA polymer. And first here I'll talk about the piezoelectric properties and how to improve the piezoelectric properties in the PLLA polymer. So basically the PLLA polymer piezoelectric property arises from the chirality of the molecule polymer chains and the non-centrosymmetric nature of the arrangement of the chains. And piezoelectric properties like arises when we alignment of the molecular dipoles, and these molecular dipoles align when we apply when we apply a mechanical stretching or a thermal annealing, and it can also be varied by the degree of crystallinity and molecular orientation and process condition. In our case, we use the mechanical stretching and thermal annealing to improve the piezoelectric property. That is the main key point here. And the challenge in the PLLA polymer is this low piezoelectric inherent properties. So the typical methods used to improve the piezoelectric properties are chemical modification and nanostructuring and molecular alignment. We go ahead with the molecular alignment to improve the piezoelectric properties of this PLLA material. And moving on to, this is our experimental setup where it involves many materials and steps. First, we start with the PLLA granules, and it has been dissolved in the chloroform solvent, and it has been casted to get the film, and this film has been cut into a small piece, and it is like uniaxial drawing has been used to which is a mechanical stretching here, and where we applied 50, 75 and then 100% strain, and subsequently it has been annealed at 80 degrees Celsius to improve the piezoelectric properties. And the obtained film has been studied with the several characterization techniques like SEM, AFM, THz spectroscopy, and XRD. Each of these techniques has provided unique insights on our results. However, now today I will talk about our THz spectroscopy study and the XRD study to correlate the piezoelectric properties. And so THz spectroscopy is a vibration spectroscopy, and it operates between lower microwave to and infrared region, and it is a vital technique for characterizing the crystalline changes in the material, and it has a capability to give insights and more details about the molecular dynamics and lattice vibrations. And these details will be helpful to know about the electromechanical properties of the material, and it is also a unique technique to identify effectively the weak forces like hydrogen bond and the van der Waals bond. So using this technique, we have studied our film. So basically, the small cut portion of this material has been strained with 50% and 75% and 100%. and it has been taken for the THz spectroscopy study. First, we put our film in the setup in this way, and we also varied the rotation angle of the setup, and the beam is sent perpendicular to the film, and we characterize the film with respect to different angle from 0 to 180 degree. And when we see the result that the unstretched film shows a symmetric response, denoting that the films are isotropic in nature. And with respect to increase in the strain, we see a peak-to-peak amplitude response. It denotes that the films are becoming more anisotropic in nature. And also that we see in maximum peak intensity at 90 degree, it indicates that the strain aligns with our electric field polarization. So now we know precisely that where exactly our alignment happens. So this film has been further taken for the analysis, and these are the summary of the THz spectroscopy result, where the refractive index clearly increases with respect to the increase in the strain. So refractive index means it is how a light propagates in a material. So when it increases, it means the film is becoming more and more dense. That is the order in the order in the material is increasing, which means that crystallinity is increasing basically. So similarly, we also see the absorption spectra that it increases with respect to the increase in the strain, denoting that the strain films crystallities are increasing. Also, you can see that the wider peaks are becoming more instinct and then prominent, indicating that the crystallinity is increasing. So we could arrive at the clear correlation between the crystallinity and the piezoelectric property here. With respect to increase in the strain, we calculated the crystallinity, which has turned out to be like increasing with the strain rate. And this we calculated using a simulation setup where from the absorption spectra, the peak has been like simulated with particular conditions, and we calculated the area under the peak of the total one, and the amorphous one is minus from the crystalline to get the crystallinity. So to further check the crystallinity value obtained from the THz spectroscopy study, we carried out the wide angle XRD. So we can see that the like again from the area under the curve, the calculated crystallinity from the wide angle XRD is almost similar to the one which has been obtained from the THz spectroscopy. And we can also see that the intensity from the like unstrained film to the strained film is increasing, indicating that the order structure is increasing. And the 2D pattern shifts from the amorphous state to slowly increase in crystallinity. So we can clearly see that with increasing strain, the crystallinity is increasing here. And further, we also tested our material with the practical application prototypes. In first case, we fixed our polymer at the bottom, and a constant force of 3 Newton has been applied with the 5 cycles, and you can see the changes in the voltage output. This is the unprocessed film, which is like showing almost zero response, and with increase in the strain, we can see the clear difference, and this result is quite good. On the other hand, when we moved with a different setup where we fix the material at the bottom, and the top is like a little bit stretched with 3% applying strain. And in this case, we see a very promising result with increase in strain rate, that the voltage change is huge. And this promising result suggests that we can also go beyond the biosensor application, like flexible electronics and etc. And the key observation here is we can tune the material properties by straining, and we can increase the piezoelectric properties of the material, and like we can apply this for biosensor applications. And currently we are trying to detect the strain in the arteric walls of the art, and this is going on. And so the future work in this is we have to still find out the piezoelectric coefficient of the material, and also study the biodegradable study. And with this, thank you for your attention.